Hi all, we are group 2. So we're going to present our study on prediction and warpage and its control mechanisms in panel level advanced packaging. So group members are myself Nitin Krishna, Mayur More, Siddesh Vishwambara and Konark Swaneshwari. So panel level packaging is an advanced semiconductor packaging technology. We know that in our conventional packaging technology, we start with the wafer, we convert it into dies, and the die is fixed to a substrate, external substrate, and interconnections are made onto it, and then we package it together. But in the case of panel level packaging, there is no substrate. This is substrateless packaging technology where we make the redistribution layers first in a carrier, and then we fix our dies onto it and we package it all together using a mold compound. The advantage of this kind of packaging technology is it enables very high density interconnects, and it gives very cost effective mass production method. So because of that, it's widely used in all the electronic devices, in smartphone, in AI accelerators, in automotive electronics, 5G RF communication modules, IoT, and advanced memory and other processor packaging. The major challenge with panel level packaging is the warpage. So warpage is the outer plane bending or deformation of the panel. So it occurs due to some internal stresses which occur during the processing. So in our case, it's thermomechanical stress, and this thermomechanical stress causes significant warpage. And with increasing size of the material, or the panel, the warpage cause issues will become more severe and severe. So this warpage leads to lithography misalignments, RDL cracking, and assembly difficulty and reduced yield and reliability. To study the warpage, we have analytical and computational method. The major issue with the analytical method, which is only available analytical method, is Timoshenko multilayer method, where they consider lateral area to be same. So in our case, lateral area is not same at all. It varies from layer to layer. The area of the chip is not same as the RDL layer, which is not same as the epoxy compound. And also the variation of the parameters with the temperature can also not be considered in the analytical model. That's where our finite element models or the computational model comes into play. In this slide, I'll be talking about one particular paper which discusses on warpage of fan-out panel level packaging using Gen 3 panel. In this paper, the author investigates the full-size Gen 3 panel, which is of the size of 650 into 550 and their extreme warpage behavior. The size of the panel you can see from the right side picture. It is considerably bigger than the normal wafers which we use for die manufacturing. And the process flow is also depicted here. It starts from a dummy glass carrier with release rail, and RDL is built onto it, and above the RDL we place our working dies, which is then covered using an epoxy molding compound, and the solder bolts are attached to it, and then we separate out different chips from it. So in this paper, we track the stress builds across the various stages, and it reveals a dramatic curvature spike after the removal of the carrier because of the sudden loss in stiffness. The methodology he has used is high fidelity 3D FEA with temperature dependent EMC and PD materials. And he has done stepwise simulation that mirrors production, which is through RDL, then die attach, then molding and debond. And also Taguchi design of experiment method is used to map out which parameters matters the most. It not only gives the importance of the parameters, and also it reduces the calculation time. It reduces the computational cost which is used upon on doing this simulation. And one specific thing only this study has considered is the gravity. It has explicitly modeled the gravity using body force loading and support table contact. When the panel becomes thinner and thinner, and especially after the carrier is removed, the gravity plays a very important role on the final warpage of the panel. Here in the result slide, you can see the author has given a comparison study between simulation which has considered gravity and without considering the gravity. The baseline design shows severe bondage warpage up to 40 mm during this experiment, during the simulation he has conducted. So, as we can expect from normal mechanical engineering knowledge, thicker chips and thicker overmoved layers dramatically boost the stiffness, and because of that, it reduces the bow of the warpage. However, whatever the thing which has come out to be the most influential factor is EMC properties, that is epoxy mold compound properties, which is CTE and modulus. Those are the two most important properties which played the important role in defining the warpage in our panels. And again, like I said, after the debond, the gravity reshaped the warpage profile, changing both the magnitude and curvature direction because of the effect caused by the gravity. The conclusion of this paper is fan out panel level packaging warpage is governed by mismatch, cure shrinkage, stiffness ratio, and gravity. All these are contributing factors on governing the warpage in a panel level packaging. And this Taguchi design of experiment offers a fast path to identify top warpage sensitive parameters like we found out here, which is EMC properties such as CTE and modulus. And again, for future, we need some reliable prediction, which definitely need to incorporate the gravity awareness, support awareness, and the curing time or the cure shrinkage also has to be incorporated into finding this warpage, which is not considered in this particular paper. And future scaling demands better EMC formulation, which considers the viscoelastic behavior of EMC compound, which is missed out in this paper. So in the coming slides, my friends will be explaining some of the papers where this has been considered and how it is affecting the warpage in of our panel level packaging.
Hello everyone, I am Mayur More. In this slide, I will explain the fundamental problem addressed in this literature and the simulation strategy used to solve it. Ultra-thin fan-out panel-level packaging substrates suffers from severe warpage. When the substrate thickness reduces to ultra-thin dimensions, then its bending stiffness decreases drastically. Because of this reduced stiffness, even moderate thermal stresses can produce large out-of-panel deformations. During manufacturing, the structure is cured at around 170 degrees Celsius and then it cooled to room temperature, that is approximately 22 degrees Celsius. During this cooling cycle, thermal mismatch stresses develop due to the difference in coefficient of thermal expansion between copper dielectric layers such as Bt or Pp and the soda glass carrier. In addition to CT mismatch, another critical factor which is polymer curing shrinkage. When the dielectric material cures, it undergoes volumetric contraction. Most conventional thermomechanical models ignore this shrinkage, but it is leads to inaccurate warpage predictions. If we look at the image on the top right, then it shows that the laminated structure consisting of copper, Bt or Pp dielectric layer and soda glass. Next to it, it is the physical image of the sample after baking, where visible warpage deformation can be observed. To analyze this behavior, the author developed a thermomechanical finite element model using ANSYS workbench. Initially, a quarter symmetric solid element model was created. Ultra-thin substrates have a very high aspect ratio, making solid elements computationally expensive. Therefore, they implemented a multi-layer shell element modeling approach. The contour plots shown below compares solid element simulations and shell element simulations. Both predict similar warpage profiles, but the shell model reduces computational time by nearly 65% while maintaining the acceptable accuracy. The key innovation of this paper is that the equivalent CT correction method. The author converted curing shrinkage into an equivalent thermal strain term by modifying the CT value. After corrections, the effective CT of the BT increased from 13 to 20.6 ppm per degree Celsius, and for PP it increased from 18 to 22.7 ppm per degree Celsius. This allows curing shrinkage to be integrated directly into the thermomechanical framework. Now, in the next slide, we will see the validation and design insights. Initially, when the curing shrinkage was not included, the shell model predicted warpage with a relative error of 27.6% with comparison to the experimental measurements. After incorporating the equivalent CT correction, the predicted warpage reduced significantly and the relative error dropped to 10.6%. This represents that 61% of improvement in prediction accuracy. This clearly confirms that the curing shrinkage is a dominant contributor to residual stress and cannot be neglected in ultra thin substrates. On the right side, we can see the graph that shows the influence of laminate CT on the warpage. The upper graph corresponds to the CT of PP and the lower graph corresponds to the variation of CT of BT. The red vertical line indicates that the CT value where the matching of CT of copper occurs. We observe that when the intermediate dielectric layer of dielectric layer CT closely matches with copper CT, the interfacial thermal bending moment reduces and it significantly reduces the warpage. The table in the center further explains this coupling effect. Model 2, which we are using of copper and Bt, has CT mismatch and higher curing shrinkage, leading to higher residual stress and larger warpage. While in the Model 3, we are using copper and prepeg, which achieves near CT matching and lower shrinkages, resulting in the reduced interfacial stresses and smaller warpage. Additionally, prepeg has a lower Young's modulus compared to Bt. This low modulus allows partial stress relaxation through localized deformation, further reducing the stress concentration. So overall, the paper demonstrates that the ultra-thin fan-out panel-level packaging warpage is governed by the coupled interaction of CT mismatch, curing shrinkage, and material modulus. The proposed framework combining multi-layer shell modeling and equivalent CT correction, which provides both the higher accuracy and practical design guidance for low warpage substrate design.
For the study, I reviewed a research paper that investigates warpage estimation in panel-level packaging using AI-assisted design and simulation. The focus is on 320 by 320 mm PLP structure and one major challenge, severe warpage. The panel-level packaging provides several advantages, including higher material utilization due to its square geometry, lower manufacturing cost in mass production, and increased in I/O capabilities. However, the large panel size makes it highly susceptible to warpage during manufacture. This excessive warpage can cause alignment issues, yield reduction, and long-term reliability risks. The paper identifies two main root causes. First, mismatch in the coefficient of thermal expansion between different materials during thermal cycling. Second, curing shrinkage of the epoxy molding compound or EMC. These effects become significant during molding, post-mold cure, and especially during debonding. To address this efficiently, the authors proposed a design and simulation framework using finite element method combined with AI assistance. A full three-dimensional PLP model was built in ANSYS APDL, including the chip, molding layer, and glass carrier, with proper boundary conditions to eliminate rigid body motion. Since EMC exhibits nonlinear and time-dependent behavior, it was modeled as viscoelastic material using the generalized Maxwell model. Dynamic mechanical analysis data was used to construct a master curve through time temperature superimposition at 122 degrees Celsius, near the glass transition temperature of the EMC. The shift factor was fitted using the Williams-Landau-Ferry equation, enabling accurate modeling of creep and stress relaxation. The process modeling was incorporated to closely replicate real manufacturing steps, molding at 125 degrees Celsius, cooling, post-mold curing for stress relief, and laser debonding. Vacuum suction during debonding was simulated using spring element with variable stiffness to mimic adsorption and release behavior. After completing the full process simulation, FEM successfully captured the characteristic fold-sided warpage pattern, which can be seen on the next page. To further improve efficiency, the study introduced an AI-assisted design and simulation approach. A database was generated by dividing the panel into 1,800 grid points and varying 5 key design parameters such as chip size, chip thickness, chip gap, extra molding thickness, and glass carrier thickness. An artificial neural network was trained using this database. Different preprocessors, solvers, and activation functions were evaluated. The optimal configuration used a standard scalar Adams solver, ReLU activation function, and 4 hidden layers with 200 neurons each, trained for 200 epochs. As you can see on the next slide, the ANN prediction showed strong agreement with FEM results, achieving low mean absolute error and low maximum difference errors. Most importantly, computational efficiency improved significantly. While each FEM simulation required approximately one full day, the AI-assisted framework reduced prediction time to around 2 hours without sacrificing accuracy. In conclusion, integrating viscoelastic process-based FEM modeling with AI-assisted prediction provides a fast, reliable, and scalable method for PLP warpage estimation. This framework significantly enhances design evaluation efficiency with maintaining physical realism. For future work, material and geometric uncertainties can be incorporated, experimental validation can be performed, and more advanced AI models such as deep learning or ensemble methods can be explored. The framework can also be extended towards reliability life prediction and packaging design optimization.
So now let us discuss how warpage can be predicted and suppressed through material optimization. So my problem statement here is during fabrication, multiple material layers such as copper, silicon, dielectric and glass are processed at different temperatures. As we can see in the figure, different layers are getting added. Since each material expands and contracts differently, a mismatch in CT is found. As a result, internal stresses build up step by step, uh, causing the wafer to bend or warp. The main contributors to this warpage are the presence of copper in RDL and thermal mismatch between silicon and glass carrier. As a result, severe wafer warpage is there occurring, yield loss is there, misalignment and reliability concerns. So the authors have proposed a framework to understand this behavior. Authors developed a non-linear finite element model that simulates the fabrication process layer by layer. This was achieved using the element depth birth technique, which allows the simulation to mimic real manufacturing conditions, where when the layer is removed it is known as the death step, and when a new layer is added it is known as the birth step. So coming on to the next slide, after predicting the warpage, the authors focused on reducing it through material optimization. They performed a parametric study by varying mainly two key design parameters: the copper volume fraction in the RDL and the CTE of the glass carrier. So using response surface methodology, they found a mathematical relationship between these two parameters and the warpage, which can be shown in the figure as well. By solving these relationships, what they results they got, they identified an optimal combination: approximately 20% copper content, because less than that will lead to adverse effect in electrical conductivity, and more than 20% is going to make our whole wafer warp. So 20% was the optimized percentage of copper, and a glass CT of 3.61 ppm, because we do not match exactly with silicon, which is having 2.8 ppm, as there are multiple layers of whether we say copper, RDL and dielectrics, all those layers. So we have to match the glass CT so that it gives the optimized way, so that warpage can be reduced. So 3.61 ppm was the best suited CT of glass. This optimized design significantly reduced warpage, and as shown in the figure, the concave warpage was reduced by 33% and convex warpage was reduced by 36%. So overall, this work demonstrates that process aware modeling combined with material optimization can significantly suppress warpage in advanced packaging systems. Coming on to the next slide, this is our references. We have used different research articles for our project, and this was all from our side, and thank you.